Hello class, this is lesson 4-7 about the absolute value functions. Now the parent function for these is f of x is equal to the absolute value of x. So if I just choose some points and I plug them in, I find that the absolute value will always be the positive integer. So then I can plot these like -2 up to 2, -1 up to 1, 0, 0, 1 up to 1, and 2 up to 2, just to start. And as you can see, this is looking kind of interesting. It's not a straight line, but it is two rays stemming from the same point. So it looks like a V. I would say it's V-shaped. And that common point where it changes direction is called the vertex. Okay? In this case, the vertex is 0, 0. Now, that's the parent function, but the general form of an absolute value function is f of x is equal to a times the absolute value of x minus h, and then on the outside of that, we would add k. So a, h, and k are all constants. If k is greater than 0, then this is telling us that the parent function is going to be moving up k units. Okay, so if it's plus 4, it's going to move upwards 4 units. If k is less than 0, then that means it's going to move down that number of units. If h, which is on the inside, is greater than 0, then the parent is going to move right h units. And if the h is less than 0, then it will be moving left that number of units. So right now we're going to graph the parent and the translation. So I'm going to just sketch the parent function here. And now looking, I have the absolute value of x, and then on the outside I'm subtracting 3. So that means it's going to move down 3 units. So I can draw the exact same function, but it has just gone down 3 steps. Now let's look at our next one. Let's sketch the parent function again. And this time it says -4 on the inside. So I'm only going to focus on that 4, which is a positive number, which means I'm going to move to the right 4 units. So instead of going down, I'm moving to the right 4 units, and it looks just like the parent function. Let's do one more where we're going to combine a couple things. So there's the parent function, but this time, notice I'm going to be doing 2 different things. I'm going to be moving up 3 units, but then on the inside, that 2 is telling me I'm going to move it to the right 2 units. So in a way, you could think of that as a point over 3 and up 2, and that's the new vertex. And I would draw the same shape as the parent function, but it is starting at 2, 3. All right, now I have some that are already drawn, and you need to write the equation of the translation. So in our first one, if I'm starting at the origin, it went down 3 units. So this means g of x I could write as the absolute value of x minus 3 on the outside. All right, my next one, it looks like it is only moving to the right 1 unit. So I could say that g of x is equal to the absolute value of x minus 1 on the inside of the absolute value. All right, for our next function, it is going down 5 units, and it's going backwards to the left 2 units. So that means that on the inside of the absolute value, I'm going to be thinking minus -2, which is the same as plus 2. And then on the outside, I will subtract 5. Okay, so that may have been a little bit confusing, but remember, it is x minus the h that's on the inside. All right, for this last one here, I'm starting at the origin, and it's going up 2, and it's going to the right 3. And so the g of x will be on the inside of the absolute value, x minus 3 plus 2. Okay. All right, so now let's look at a vertical dilation. So remember, we've done dilations before, and so this is either going to be stretching or it's going to be compressing the function. So for a vertical dilation, we could say that if the absolute value of a is greater than 1, so that a that we're talking about is the number that's on the outside, then the parent is stretched vertically. Okay, so it's going to be looking a lot, I guess maybe more skinnier than the parent. And if the number is between 0 and 1, then the parent is compressed vertically. So this means it looks like it's getting flattened. Okay, so I'm going to draw the parent here, and then I'm going to figure out how to draw g of x. So it's 3 times the absolute value of x. So I'm going to just pick 3 points here and plug them in. 3 times 1 is 3, and 2 times 3 is 6. And now I can plot all 3 of those points, 0, 0, and then 1 up to 3, and then 2 up to 6. And I can also reflect those on the opposite side just to help me out and draw my line, and look at that. This definitely looks like it's being stretched vertically. I noticed that 3 on the outside was greater than 1, so that makes sense. So I could say that the function, the parent function, is stretched vertically. Okay? So now for my next example, I'm going to go ahead and graph the parent function again. And g of x is equal to 1/2 the absolute value of x. So with those same points, let's plug it in. 1/2 times 0 is 0. 1/2 times 1 is 1/2, and 1/2 times 2 is 1. So I can plot all 3 of those points there and reflect them on the opposite side and draw my line through those points. And look at that. It is starting at the same place, but it is being compressed vertically. It looks like it's getting more flat. So I would say that the function is compressed vertically. So now let's look at a horizontal dilation, which is fairly similar, but this time we say that if the absolute value of a is greater than 0, then the parent is being compressed horizontally. And the opposite goes, if the absolute value of a is between 0 and 1, then that means that the parent is going to be stretched horizontally. So that means it looks like it's going to be flattened horizontally. So let's go ahead and graph the parent function. And then we're going to choose values for g of x, like 0, 1, and 2. 2 times 0 is 0, 2 times 1 is 2, and 2 times 2 is 4. So I'm going to plot those 3 points, 0, 0, 1, 2, and 2, 4. And then I can reflect them on the opposite side and connect my dots. And there you go. But this time, I would say that f of x is, that's the parent, is being compressed horizontally, okay? So it's not being stretched horizontally. This last one here, I'm going to plot the function for the parent, and then I'm going to pick those same points and plug it in so that the absolute value of 1/4 times 0 is 0, 1/4 times 1 is 1/4, and 1/4 times 2 is 1/2. All right, now let's go ahead and plot those 3 points. So 0, 0, 1 just up to 1/4, 2 up to 1/2, and then I'm going to reflect those on the opposite side of the y-axis as well. And then I can go ahead and connect those dots to draw my lines. Okay, there we go. So this is definitely being flattened. It's being stretched horizontally, which means it's being stretched closer to the x-axis. Okay? Let's move on now to reflection across the x-axis. So visually, what you're thinking of is the function that's pointing upward. You would flip it upside down, and now it's opening downward. And so what we would say mathematically is that the graph of negative a times f of x is the reflection of a times f of x is equal to a times the absolute value of x. So that's just really saying that a times the parent function. And this is going to be reflected across the x-axis. So we're going to do like we've done before. We're going to graph that parent function. And now we need to graph g of x. So to begin, since we are adding 3 on the inside, that means we're going to be moving it to the left 3 units. So I'm going to start with -3 for the values that I'm choosing because that's going to be the vertex. So -3 plus 3 is 0. -2 plus 3 is 1 times -1 is -1. -1 plus 3 is 2 times -1 is -2. And then 0 plus 3 is 3 times -1 is -3. So now we can go ahead and plot those points. So I have a variety of them. And then I can reflect them on the opposite side. And there you go. As you can see, it is the same shape as the parent function, but it is upside down and it's been translated to the left 3 units. So to describe this, I would say that the function, the parent function, is reflected across the x-axis, and it was also translated 3 units to the left. And that would be my description. All right, now we're going to look at a reflection across the y-axis. And again, this is kind of similar to what we just did, but if you're visualizing this parent function and you're reflecting it across the y-axis, it might not even look like it's being reflected at all because it still is above that x-axis. So what we're going to write down is that the graph of f of negative ax is what we call the reflection of f of ax, which is equal to the absolute value of a times x. And this is going to be across the y-axis this time. So let's go ahead and graph the parent function like we've been doing. You're probably getting good at it. And then notice that on the inside, we're going to be multiplying it by -3. So it doesn't matter what values I choose. So again, I can just pick 0, 1, and 2 for the points that I'm going to plug in. So -3 times 0 is 0, which the absolute value of that is still 0. -3 times 1 is -3, and the absolute value of that is +3. And -3 times 2 is -6, but the absolute value of that would be +6. So now we can go ahead and plot those points and reflect them on the opposite side of the y-axis. And this is what our function looks like. So it doesn't necessarily look like it's being reflected, even though it is. The parent is reflected across the y-axis. And because that -3 is on the inside of my absolute value, that means that this function is being compressed horizontally. Okay. Let's go ahead and move on to our final examples. We're going to graph the parent function in g of x. This time we're going to describe the domain and the range. So I'm graphing my parent function, and then when I look at g of x, it's equal to the absolute value of 3x minus 6. So when this happens, when you have a coefficient before the x, I'd like you to factor it out. So that's really 3 times x minus 2, which means that the parent function will be moving to the right 2. So I'm going to start by picking values based around 2, like 2, 3, and 4. So now when I plug those in, 3 times 2 is 6, and 6 minus 6 is 0. 3 times 3 is 9, and 9 minus 6 is 3. And then 3 times 4 is 12, and 12 minus 6 is 6. Now that that is done, I can go ahead and plot those 3 points. 2, 0, 3 up 3, and then 4 up 6, and I can reflect those on the opposite side and draw my lines. So look at that. It has been moved to the right 2, but it has also been compressed horizontally. So if I'm going to explain the domain, this has all real numbers that you could choose for the values of x. For the y values, it is all of the real numbers that are greater than or equal to the value of 0. So notice there are no negative y values for this function. All right, our last example, let's go ahead and plot the parent function again. And now to graph g of x, it's equal to negative absolute value of x minus 3 plus 5. So that means it's going to be reflected over the x-axis. We're going to move to the right 3, and it's going to move up 5. So we have a lot going on. So I'm going to pick values based around 3. And so when I plug that in, 3 minus 3 is 0, plus 5 is 5. 4 minus 3 is 1, so that's negative 1 plus 5 is 4. And then 5 minus 3 is 2, so negative 2 plus 5 is 3. So now we can go ahead and plot those 3 points. So 3 and then up 5, 4 up 4, and then 5 up 3, and reflect them on the opposite side of 3, 5. So notice this new function is going downward, okay? And it has been moved to the right 3 and up 5. So the domain, again, for the x values could be all real numbers, but for the y values, there is a limit. All real numbers that are less than or equal to 5, okay? Because 5 was at the vertex, and that's it. So I know this was a long lesson, but please let me know if you have any questions when you come into class.